Alright, so today we're going to be going through the absolute value function. Now, absolute value is a concept that you may not have heard before, but trust me, it's very simple. We're going to see that right now. What we're going to go through is how to solve these inequalities. So absolute value introduces another complexity when solving inequalities. You probably know how to solve basic inequalities like, for example, x minus 3 is less than, for example, I could do, I don't know, 2 over x. Yeah. So, for example, you should probably be able to solve something like this. You can use your inequality rules and be able to solve for a set of x values that satisfy this inequality. Okay? So, by introducing the absolute value, we are actually going to make these problems more difficult. But it turns out that the absolute value function is very important for what we're going to be doing after. It's very important to know how to graph the absolute value function in particular. Let's see. I think after that we're going to do some graphing, and that should take us to the end of the lecture. Okay, so let's get started. The first thing is the definition of absolute value in the notation. So given some number x, okay, we denote by the vertical bars beside x the absolute value of x. Okay, and all this means is I'm going to take the positive, I'm going to take x and make it positive. So take x, make it positive. Right? So clearly this makes a lot of sense if x is a negative number, right? You're just taking the negative number and you're making it positive. You preserve the same number, you just change the sign on it. If it's positive, then it's clear that this function does absolutely nothing. So we can actually define a function, f of x equals absolute value of x, and we'll define it piecewise. So that's why I introduced the piecewise function notation earlier. So what we'll do is that if x is greater than 0, so in other words, if x is positive, then it does nothing. Right? So in other words, I could just say, you give me x, and I'll output x. Okay? If it's negative, right? Well, that means our number x is a negative number. So in order to flip the sign, we can just add another negative onto it. So by doing negative x, we get the positive component. So let's just do some quick examples. If I have absolute value of 6, that's obviously 6. 6 is greater than 0, so we do nothing. We just get x. If our input is negative 3, well, now negative 3 is less than 0, so we're going to take the negative of negative 3, and that gives you 3. So clearly, all the absolute value function does is it takes the number and spits it out. Okay? It ignores the sign. That's the easiest way to remember absolute value. Okay? So this means that we're going to have to input these into our equations and inequalities in a rather clever way. So what we're going to do is cover what it means in a very simple case for x to be less than 5, for example. Okay? So I want to take the absolute value of x and see what values of x satisfy this inequality. Absolute value of x is less than 5. Okay? So what does absolute value mean again? It means I'm just going to take x and I'm going to ignore the sign on it. So if you think about it a bit, try and just reason out what values of x would work. And you should come out with every value between negative 5 and 5. Okay? So just think about why that must be the case. And then we'll continue. So what we're doing now is we're just going to say that x is between negative 5 and 5, and look, all of a sudden we have really easy inequalities to solve, right? Now, in this case, we pretty much have the answer already, but of course I could have made this more complicated. For example, I could have made like an x plus 3 and less than, let's do another number. Let's do 8. Okay. So this is the same thing as x plus 3 being between negative 8. X plus 3 is between negative 8 and 8. Okay. So then what you can do is, because this is a regular old inequality, you can just subtract 3 from both sides, and you get negative 11 x 5. Okay? So hopefully that's not too difficult. The other problem, it's a very similar problem, is what if I want all the values where absolute value of x is greater than 5? Right? So just think about that one for a second. And you may realize that there are actually 2 solution sets. So clearly every number x that is bigger than 5 works, right? Because if x is bigger than 5, it's a positive number and it's bigger than 5. Like the absolute value function doesn't do anything to it. But the other option is x is less than negative 5. And the reason why is because if x is less than negative 5, the number itself is going to be bigger, and the absolute value function is just going to ignore the sign. So you still have that the absolute value of x is bigger than 5. Now this is a really important thing. It's this one or that one. Okay? Clearly, it can't be both, right? The thing is, in math, when we say or, we usually mean this one, that one, or both. And we're going to come across some examples where we actually have to contend with that issue. So let's just make a brief deviation here to explain the difference between this and that, right? So here we have a condition that says x is between, actually let's do less than first. X is less than 5, and at the same time x is greater than negative 5. Okay? Now, this is the exact same thing as what I've written in purple here. All I'm saying is that these 2 statements combined, when you connect them with and, it says the exact same thing here. Whereas here, we have x is greater than 5, or x is less than negative 5. Okay? So this, with an or, says the exact same thing as this. Right? So all we require is that either this condition be true or this condition be true. But in this case, both conditions must be true. I can't just take any number less than 5. I need to take a number that is less than 5 and greater than negative 5. Okay? But this one, it can be either or. Okay? It doesn't have to be both. So now that we've gotten that out of the way, let's do a more tricky example. So I'll start off with one that involves a rational function. So let's see. Okay. So the first example I have is x plus 4 over absolute value of x plus 2 is less than 6. Alright, so if this is the first time you've just learned about absolute value, I don't expect you to be able to do this right now. So we're going to work through it together just to give you a bit of a feel of how you would go and solve these problems. But before we do that, let's tackle the somewhat easier problem of the following. Let's just remove the absolute value sign, right? Your grade 11 knowledge should allow you to solve something like this for x, right? How you would do this is you would just take this and multiply up here. So x plus 4 is less than 6 times x plus 2. We'll just keep in mind that x cannot be equal to negative 2. I'll just keep that up here in the top so we remember at the end, right? So all we would do is we would expand this out. This becomes 12x plus 6x plus 12. This here is x plus 4. You know, if you juggle things around, you'll get 5x is greater than negative 8, or in other words, x is greater than negative 8 over 5. And nothing too fancy happened there. Okay? So just think about for a second, what is the difference then between this question and that question? Well, with this one, we just have the absolute values, right? That's literally the only difference. So our final answer should have something to do with this, right? Because we just said that if this value here is positive, if x plus 2 is positive, the absolute value does nothing to it. So we should at least in some case have that x greater than negative 8 over 5 is a solution. Okay? So let's get that out of the way. And we didn't end up having to worry about, well, we do have to worry about x not being equal to negative 2. Actually, no, we don't, because our final answer was x must be greater than negative 8 over 5, right? But if you think about negative 8 over 5 in relation to negative 2, right, on a number line we have negative 2 is over here, negative 2 is equal to negative 10 over 5, and negative 8 over 5 is just a little bit less, right? So on a number line, if we want x to be greater than negative 8 over 5, that's just every number from here on out, okay? Right? Because x just has to be greater than negative 8 over 5. Alright, so that being said, let's now try and tackle that one. That one's a little trickier, okay? So the same rule applies as with the regular rational expression. If the denominator is 0, we're going to have a big problem. So let's just straight away make a note that x cannot be equal to negative 2, and see what we can do from there. Okay? So the first thing I'm going to do is I'm going to try and think of what would happen in two different scenarios. And my two different scenarios are the things that happen with the absolute value bar. Okay? And they are the following. So what happens if x plus 2 is greater than 0? Well, by the absolute value function, nothing. Right? But if x plus 2 is less than 0, we have to flip a negative on it, right? So negative x plus 2. So this x plus 2 would have to become a negative x plus 2. So why don't we consider those two cases separately? Okay? So here's how we're going to solve this. We're going to consider the two cases separately. We're going to first consider the case when x plus 2 is greater than 0. Wait, hold on a second. Don't you just see something there? If x plus 2 is greater than 0, that just means that x is greater than 2. And similarly, this one says x is less than negative, sorry, this is a negative 2. X is greater than negative 2, and x is less than negative 2. So maybe this is actually what we want to deal with, right? We want to deal with the cases when x is greater than negative 2 and x is less than negative 2. So let's think about that for a second. Okay, so we know that if we're in this case up here, nothing happens. So let's just pretend we're in this case up here. Let's pretend we're only dealing with values of x that are greater than negative 2. So then we can ignore the absolute value symbols, and we can just continue about it like nothing happened. Okay, like the absolute value symbol was never there to begin with. So what does that give us? X plus 4 over x plus 2 is less than 6. And we just did this. We literally just did this. And we came up with the answer that x has to be greater than negative 8 over 5. I believe that was the answer. Yeah, x is greater than negative 8 over 5. This is just reiterating what we did a few minutes ago. Okay. Now, the only thing that the absolute value brings into here, as I've just showed, is the second situation. So what happens if x is less than negative 2? Well, that means that we have to replace what's in here with the negative of that. So what is the negative of x plus 2? Well, negative of x plus 2 is equal to negative x minus 2. Okay? Be very careful about that. It is not x minus 2. The negative of x plus 2 is not x minus 2. It is negative x minus 2. You have to distribute the negative sign among each part that you add. Okay? So now we can replace the x plus 2 with a negative x minus 2, and we get this. X plus 4 over negative x minus 2 is less than 6. Now what? We have a problem, right? Because remember, the denominator can never be 0. So we have to put in the corner that x cannot be equal to 2. Because if, no, there's no problem. There's no problem. Yeah, there's no problem because the only thing that could go in here that would make this thing 0 is a negative 2. So we already got that one covered. My bad. Okay, so let's multiply both sides by negative x minus 2. So x plus 4 less than 6 times negative x minus 2, brackets for insurance. Then we'll continue. X plus 4 is less than negative 6x minus 12. And then we can do some manipulations. I believe you'll come up with 7x is less than negative 16, or x is less than negative 16 over 7. Okay? So, what do we have? We have two conditions, right? We have two conditions. We have that x is either greater than negative 8 over 5, or x is less than negative 16 over 7, right? Let me just be super explicit about what happened. So this is like case 1, and this is case 2, okay? And what we have is that case 1, we assumed that x was greater than negative 2. And in case 2, we assumed that x was less than negative 2. We have to be very careful here. If we don't put all this information down, we're bound to make a mistake eventually. Okay, and there are lots of examples that you could come up with that if you don't consider these two things, you're going to get into trouble. Okay, so what is going on here? The easiest way to see it is to draw a number line. So let's do that again. So let's draw negative 2 on a number line. Negative 2, let's just say it is here. And negative 8 over 5, well, that's a little bit bigger than negative 10. Okay, it's bigger than negative 10 over 5, which is negative 2. So again, negative 2 is negative 10 over 5, and this is negative 8 over 5. Negative 8 over 5, right? And we just said that x has to be bigger than negative 8 over 5. So that means our solution set is everything here. So in the end, this x is bigger than negative 2 didn't really matter. We just need to satisfy both these conditions. This and that. Okay, so here's one solution. Our solution is that x is bigger than negative 8 over 5. And I'll put a circle here to indicate that we are not including negative 8 over 5. We are not including negative 8 over 5. On the other hand, here, we have x must be less than negative 2. Right, so let's draw negative 2 on a number line again. Here's negative 2, here's 0. Okay. And where is negative 16 over 7? Well, negative 16 over 7 is just going to be a little bit over here. Right, so let's call this negative 16 over 7. The reason being because this is negative 14 over 7, and that's negative 2. Right, so negative 16 is going to be a little bit more to the left. And our requirement was that x is less than negative 2. Okay, so it's somewhere in this region. But then we have this other condition here that says x needs to be less than negative 16 over 7. So let's just shift this. So that means our solution set is everything to the left of negative 16 over 7. And let's draw that in. Remember, we're not including negative 16 over 7. It's just everything to the left. Everything to the left of it. And that would be our answer. So our answer, we will write in set notation. This is where the set notation becomes really important, because it's really difficult to write this in interval notation. Set notation is just much easier to do. All right, so we're looking at the set of x values such that x is greater than negative 8 over 5, or x is less than negative 16 over 7. Okay? If you've never seen absolute values before, this example might be a little bit overwhelming, but at its core, all you're doing is twice the amount of work that you had to do when the absolute value bars were not there. So again, the answer is x is greater than negative 8 over 5, and x is less than negative 16 over 7. Now notice that just doing it without the absolute value bars actually gave us half of the solution. Right? This is what we originally came up with when we tried to simplify the problem by removing the absolute value bars. So it wasn't all for waste. In fact, we actually had to do the exact same thing right here. Okay, so just keep an open mind about that. The only part that we had to do extra work was for the case when x plus 2 is less than 0. So let me just illustrate the general strategy that we took here. The absolute value is a bad thing. We need to get rid of it. That's your first step in solving these problems. You get rid of the absolute value. How do you get rid of the absolute value? Well, you need to consider whether the thing inside it is positive or negative. And that gives you this or that, right? So here's the case when it's positive, and here's the case when it's negative. But each of these are simple inequalities that you just have to solve. In this case, it gives you x is greater than negative 2, and x is less than negative 2. Those are your two cases. Okay? Then you break it up into those two cases, right? Now, of course, when x plus 2 is positive, like we mentioned before, the absolute value symbol does absolutely nothing. When x plus 2 is negative, then you have to change something. You have to put a negative sign in front of the x plus 2. And then you just do the work from there. You get one solution set. You make sure that it coincides with this and that. So x cannot be negative 2, and x must be less than negative 2. How did I get this? Remember, I just look over here. Right? It's an equivalent condition. And then you just get these two sets. Put it in a set notation, and you're done. Okay? That's how you solve these problems. So because that might be a little bit overwhelming, we'll do another one. Of course, we'll ramp up the difficulty a little bit. Okay? We are going to now involve quadratics. But the procedure, at its core, is really just the same thing. Okay, so let's do that. Oh, and by the way, if you wanted to, you could go on Desmos and graph the function x plus 4 over absolute value of x plus 2, and just check wherever this function is less than 6, right? And you'll find that it is less than 6 exactly in the region where I described earlier in the solution. Okay, so you should actually go on Desmos and just check out how weird this graph looks first of all, and then just make sure that our solution was right. I've checked beforehand that the solution is okay, but you should go and just look at it for yourself. Maybe try and do it on your own for practice, and then use Desmos to verify. Okay. Okay, so the next example I have is this: x minus 6 over absolute value of x squared minus 4. And now I want it to be greater than negative 2. Okay? So again, this one's tricky. This one's actually quite tricky. So here's how we're going to tackle it. Okay? We're going to do the exact same thing as we did the first time. So first of all, what cannot go in there? 2 cannot go in there, right? So if I want to solve just x squared minus 4 equals 0, right? Because the absolute value of 0 is just 0. So I'm just going to solve the equation inside for 0. X squared minus 4 equals 0 gives you two solutions. This should be clear by now that the solutions are x equals 2 and negative 2. Okay? So that means that we cannot have x equal to 2 or negative 2, because if we did, the denominator would be 0. Bad things happen. Okay, so let's just put a big reminder up there. X is not equal to negative 2 or 2. Okay. Next step, we're going to do the same thing. We're going to consider the case when x squared minus 4 is greater than 0, and the case when x squared minus 4 is less than 0. Okay? Remember, in this case, we actually don't have to do anything. I'm going to put an equal sign up here just to cover the 0. Okay? We don't have to change anything here. But here we do have to change something. Okay? So let's solve each of these individually. Okay? This just says that x squared is greater than or equal to 4. Okay? And we know that there are two solutions for this. Okay? You can see this just by graphing it, right? So here's 4. And x squared minus 4 is like what? It's like, it looks like this, right? Where that's minus 4. So you're just asking for solutions. So you're asking for solutions when this function is greater than 4, okay? Actually, sorry, my bad. Yeah. So you're looking for when x squared, the function x squared, is bigger than 4. Okay. So here's 4. So it's like you can just see from the graph that it's like everything beyond this point and everything beyond that point. And you should be able to tell that this here has x value -2, and this here has x value 2. So it's all the values to the left of -2 and all the values to the right of 2. So this means x is less than -2 or x is greater than 2. Okay, this is a type of equation that you should have been able to solve from grade 11. Okay. So clearly the absolute value is just gonna mess things up, make your life a lot harder. Okay. So once you've taken a moment to digest that, let's move on to the next one, which is this x squared minus 4 is less, x squared is less than 4. Okay. So to solve this, all we have to do is, again, you could look at the graph. You just want to know when x squared is less than 4, right? And that is in between these two points. That's -2 and 2. So x must lie between 2 and -2. Okay. Generally, the solutions here, they have to all together fill up the entire real line. Okay. The only exception is the points that we explicitly said could not satisfy this equation because it would result in a calculator error. So you could have just immediately jumped to this from here if you were comfortable with it. Since this is our first time, we're not going to jump any steps. We're just going to solve each part the way we're supposed to. Okay. So just like last time, we get a case 1 and a case 2. This is a case 1. This is a case 2. Okay. So in case 1, we don't have to change anything. Lucky. So all we do is x minus 6 over x squared minus 4 is greater than -2. Okay. Now what? You can take this, bring it over here. X minus 6 is greater than -2 times x squared minus 4. And then from there it just becomes a game of solving the quadratic. Okay. So just to do it quickly, I've got -2x squared plus 8. You should pause the video and work through this part on your own. You should be capable of doing this from your grade 11 knowledge. Okay, so we get 2x squared plus x minus 14 is greater than 0. Okay, this part I remember is difficult. All right, so now that we've gone up to here, we want to be able to solve this. You could do the ways that you had in grade 11 of just completing the square or something. But I'm just going to tell you the answer. I personally didn't complete the square. I just looked it up on Desmos. All I'm looking for are the zeros here, right? Because once I know that, I can solve this inequality. It turns out that the zeros are -2.908 and 2.408. Okay, I just got that from graphing. Now, just consider the geometry of this parabola. You know that this parabola has to open upward, right? It's going to be a U shape just by looking at the first term here. So you know the zeros are here and here, and you can just very roughly sketch it. So -2.908, and here is 2.408. And if I were to just sketch my parabola, it would look something like that. Okay? Sorry about the drawing. But anyways, our question is asking for when this parabola is greater than 0, and just looking at the picture you can tell that it's greater than 0 for any number here and any number there, right? So our solutions are, let me just write it in red, so just box this off in a corner. This is not part of our question, this is just something that we needed to do to find the roots, okay? But our actual solution is x is less than negative 2.908 and x is greater than 2.408. Okay? Now let's see how they match up with our initial conditions. So here we have negative 2, here we have 2 and 0. Okay? So our first condition says you must be less than negative 2.908. So negative 2.908 is just a little bit to the left here. So it's everything here. So we're good. Our second condition says bigger than 2.408. And 2.408 is just to the right of 2. And it's everything here. And this whole time we've stayed within the condition that x is either less than negative 2 or greater than 2. So we're fine. We're actually fine. Okay? Yeah, so let's just keep that on the side. I'll put it right here in the box. So we get x is less than negative 2.908 or x is greater than 2.408. Always a good idea to put your ands and ors. It will help in the last step because this question, the last step can get quite tricky. Oh, I don't want to do that. I'm erasing the question. X minus 6 over x squared minus 4. Greater than negative 2. Okay, so now we're going to slap a negative on that. So if I put a negative on x squared minus 4, I get negative x squared plus 4. So I'll replace that in. I get, when I'm solving, I get x minus 6 over negative x squared plus 4 is greater than negative 2. Now this one, I've done the first one for you. I want you to go through this and make sure we end up at the right answer. I'm not going to go through all the steps. It's going to save us a good bit of time. But eventually you should get negative 2x squared plus x plus 2. Okay? And this you want to be greater than 0. Okay, so now we want to solve this equation right here. And of course I didn't do it the hard way. I just graphed it and I got to solve this equation. The answers are simply x equals negative 0.781 and x equals 1.281. Now we're going to use our graphical intuition here once again. So remember, we're trying to solve for when this quadratic is above 0. And we know that the roots are 1.281 and negative 0.781. So if I'm just going to graph this, it's going to look something like that. It really doesn't matter. The point is, all we want is to find when this quadratic is above 0, and from our really rough sketch, it's clear that it's in this region here. So in other words, when x is between negative 0.781 and 1.281. So that's when this inequality will be satisfied. And then just double checking that it lies within our initial constraints. Remember that we needed x to be between negative 2 and 2, but this interval here is comfortably within that range, right? Negative 2 is like even further down here, and 2 is even further down there, so we're fine. Okay. Just quickly, if there was an issue, all we would have to do is modify these constraints. But that's a very extraordinary situation. That usually does not happen. Okay, so just make a box right here, and I'm going to erase this side of the board. So we have that x must be between those two numbers. And negative 0.781. Now you may be wondering, how do I know when to use and or? Right? Here I have an or statement. Either x has to be less than negative 2.9 or greater than 2.4. Here I said x has to be between the two. That's an and statement. The reason why I know is just because of the natural logic of the statements, right? So here we deduce that these two must be true. Well, that can't be, so it has to be an or, right? Because it's not possible for a number to be less than negative 2.9 and greater than 2.4 at the same time. So it's naturally an or statement. The decision, whether it's and or, that should arise naturally out of the logic. Okay, so let's finish this off then, just by writing our solution set in set notation. Remember, throughout the process, we've made sure that this is always satisfied, and we've also made sure that this and this are satisfied when they need to be. So what I have in the boxes here is actually all we need, right? Okay, so what does that mean? We're done. We just have to very carefully analyze what these two boxes are saying, right? Because they are both correct, right? When x is greater than 2 or less than negative 2, this is the solution that we should be looking at. Or when x is between negative 2 and 2, this is the set of solutions that we should be looking at. So let's just quickly graph it on a line. Okay. All right, so here's 0. We're going to graph the first one in purple. So this says, let's get negative 2.908 here. So we need solutions that are all here and solutions that are all here. So we want all these values of x. Another value of x that we need is found in here. So we need to get negative 0.781 and 1.281. 1.281. Okay? So our solutions can also lie in here. So what our work has determined is that if you pick a value of x in either this section, or that section, it will satisfy the equation. Let's just give it a go, just to get a feel for it. Well, here's a really easy number. Let's just pick 0. 0 is in our solution set. So if we put in 0 here, what does that become? Well, that just becomes 0 minus 6 over 0 minus 4, absolute value is greater than negative 2. And then this in the bottom just becomes 4, so we get negative 6 over 4 is greater than negative 2. And is that true? Well, yes, this is just negative 3 halves. And of course, it's greater than negative 2. Okay? Let's pick another easy number in here. The reason why I'm doing this is I'm just illustrating how you should double check your work. This is a foolproof way of checking. Okay, so just pick some number here, like 3. 3 works, right? So if I put 3 for x, I get what? 9 minus 4 is greater than negative 2. This is minus 3 over 9 minus 4 is 5. Absolute value of 5 is 5, so we just have 5, right? So now we want to know, is negative 3 over 5 greater than negative 2? Well, yeah, of course, because this one's greater than negative 1. Okay, so that's good. And just for fun, let's do one more. We can choose negative 3. So let's choose negative 3. So we put negative 3 minus 6 over, again, negative 3 squared is 9 minus 4. And then we want to check if this is bigger than negative 2. What does that give? Well, it gives negative 9 over, and this is 9 minus 4 is 5. Okay? And this is obviously bigger than negative 2 as well. Okay. So I think I've managed to complete this successfully. You should check on Desmos, make sure that the solution set that we've got is right. So all you have to do is graph this, and also graph the line y equals negative 2. And then just check where this graph is bigger than negative 2. And if we're right, it should be bigger than negative 2 here, here, and here. This is the x-axis. This number line that I've drawn is like your x-axis. So what we found is that the solutions are satisfied wherever the purple is. So that means our solution set, we can write it as x such that x, I'm not going to write x as an element of the reals. X is between negative 2.908. We have three sections. We need either x is less than 2.908, or x is between those two numbers. So let's do it like this: negative 0.781 and 1.281. And the last one is x is bigger than 2.408. Okay? Right. All right, so that's our set. That's our solution set. Okay? And we're done the problem. So, I think those two examples, they are pretty difficult. But it's good that we've done them because they represent probably like the most difficult part about absolute value. Let me just go through some properties of the absolute value first before we go into graphing, because there are some very easy to make misconceptions that happen with absolute value very, very frequently. Okay? At the same time, there are some laws that you should know. So let's just go over those really quickly. We need to cover the three basic operations. Plus, minus. Plus and minus, they're the same thing at the end of the day. Multiplication and division. Okay? So here's our first question. What is absolute value of A plus absolute value of B? You may think that it is equal to A plus B. You may hope that it's true. But a quick bit of thinking will get you that it's not true. And in fact, I want you to think of an example where this is not true. It's not very difficult to think of one. You just have to play around with some numbers, and eventually you'll get it. But clearly, if A and B are positive, then this is true, right? Because if A is positive, then this is just A. If B is positive, then this is just B. And absolute value of A plus B, if A and B are both positive, is just A plus B. So it's sometimes true, but in general, it is not true. So this thing is something you should be really concerned about, because a lot of people make this mistake. Do not make this mistake. However, multiplication behaves a little nicely. Absolute value of A times absolute value of B is indeed equal to the absolute value of AB. Okay? You can just think about it for a while, play around with some numbers, and you'll find out that that's true as well. Okay? And really the reason why is because what you're doing here is you're taking a positive number and you're multiplying by a positive number. Okay? When we're multiplying two numbers together, if we're going to just ignore the signs, the actual number is going to stay the same all the time, right? 7 times 8 is 56, but negative 7 times 8 is negative 56. The 56 is still there, right? When I do this, however, the output is still going to be positive, and the actual number itself is going to stay the same. So in my example, I had 7 or negative 7 times 8 is equal to negative 7 times 8, and this is negative 56, but the absolute value turns into a 56. And here we have 7 times 8, which is 56. Okay, so the multiplication property is very nice. Now, given that multiplication and division are closely related, you may also suspect that if I do A over B, this is the exact same thing as the absolute value of A over B. And you would happen to be right. It works exactly the same way. Really, all you're doing is you're replacing in this formula B by 1 over B. And like, it's the same thing. Okay? So those are some properties that you should just be sure. The big one's the addition one, because the addition one's an easy one to mistake. So make sure you understand why that thing that I wrote on the board is not true. Okay. So to finish it off, I know I've gone a little long on time. We're just going to go through some graphing. The good thing about graphing absolute value is that it's really easy. If you just remember your rules for graphing in grade 11. So recall, if you have the function a, b, x minus, I believe it's c plus d. I don't know, I'm just putting the letters there. Then A does a vertical stretch. B does a horizontal, it does like a squishing effect, a horizontal squishing effect. C is translation, left and right. And D is a translation, up and down. Okay? So we can just apply those exact same principles here, except now instead of just some random f, we're going to pick f of x is equal to absolute value of x. Okay? So let's see some examples of how this works. But to do this, we need to know what the parent graph looks like. So absolute value of x. We know that when x is positive, it does the exact same thing. So you give it x, and the absolute value spits out x. So it's just going to look like the line y equals x. But over here, what's going to happen is that where the line should continue going, it's actually going to flip it up positive, right? Because the absolute value only outputs positive. So this is what the absolute value function looks like. Okay? And now what we're going to do is we're going to do some examples where we play around with the translations just to see what happens to the graph. Really, all of it is very intuitive, and if you've understood the translations and transformations from grade 11, this should not be that much harder. Okay, so let's just do an example. Okay, so quick example. It's going to involve like let's do like 2 of them. Okay, so let's do like or 3, I guess. Yeah, a times f. Okay, let's do negative 3 times x minus 2 plus 1. Okay, very simple example. We want to graph this. So let's just draw our parent graph first. This is what absolute value x looks like. Okay. The negative 3 will squish it by 3, and it will stretch it vertically by 3, and it will flip it in the x-axis. So if we do that, it's going to look a little skinnier like that. Okay. Let's just keep track of a point. Let's keep track of that central point, and let's also keep track of the point that was originally 1, 1, right? Because 1, 1 is originally on here, because if you put a 1 in here, the output is 1. So we can actually track what happens to this point here. If we squish it if we stretch it vertically by 3, then this 1, 1 is going to turn into 1, 3, and then we're just going to reflect it down here. So this is the point 1, 3. Okay. Next, we have to translate to the right by 2, and then we have to translate up by 1. So let's do that. We're going to move. This is sort of like the central point that you can use to base all your calculations off of, right? So I'm just going to move this vertex here 2 to the right, and then 1 up, okay? And that's going to give me my final graph, which I'm not going to draw on the same picture. I'm just going to draw it here. Sorry about that. There we go. Okay, so this point that was originally 0, 0 is going to get moved up until 2, 1. So we have here 2, 1, and here's that point. And then we're going to draw the slants. Okay, and we're going to figure out where our point 1, 3 went as well. Although maybe you could think of that right now while I'm drawing this. Okay. It looks something like that. Okay. Our point 1, 3, it also gets translated 2 to the right and 1 up. So if you just think about it, it becomes 3. Sorry, this should be a not a 3. It should be a negative 3. My bad. You translate it 2 to the right and then 1 up. So this should actually be the point 3, negative 1. So 3, negative 1. That's where our point went. This is just something that you can use while you're graphing. Some more useful information, though, might be the x and y intercepts. So let's just quickly think about that. What would the x and y intercepts be? Well, to solve for the y-intercept, right, what we need to do is we need to figure out what happens when I plug a 0 into this expression. If I put a 0 in here, I just get, what, negative 3 times negative 2 plus 1. Absolute value of negative 2 is just 2. And negative 3 times 2 is negative 6. Negative 6 plus 1 is minus 5. So this intersects at minus 5. Okay. Now we want to figure out where it intersects here. And that just means that f of x is equal to 0. So we are solving now for when this equation is equal to 0. We can do that very simply. It's actually a lot easier than the inequalities that we just worked through. I'd encourage you to try doing this yourself. just pause the video, try this yourself, and you should be able to get pretty quickly, because it's literally exactly what we just did. -1, divide both sides by -3, you get x minus 2 is equal to 1/3. Okay? Now, with the absolute values, again, you need to consider what happens when x is less than, right? Okay, so now when is x minus 2 less than 3? So we have a case 1. Case 1 is where x minus 2 is greater than 0, and case 1 is when x minus 2 is greater than 0. Case 2 is when x minus 2 is less than 0. Okay? This case, we get x is greater than 2. This case, x is less than 2. Okay? That's just from rearranging these formulas. Okay? So let's just work on case 1. What happens in case 1 is that we can just replace x minus 2 absolute value with x minus 2. So we get x minus 2 equal to 1/3. And then this just gives us very simply that x is equal to 2 plus 1/3. And if you want to be fancy, it's equal to 7/3. Okay? So one of those points is 7/3. The other one, again, we have to replace the x minus 2 by a negative x minus 2. So let's do that. We'll replace it by negative x minus 2. So negative x minus 2 is equal to 1/3. Throw a negative on the other side. Add 2 to both sides. So we get x is equal to negative 1/3 plus 2. If you want to be fancy, this is 5/3. Okay? And so we actually have our two x-intercepts here. 7/3, 5/3. Now, I've added a lot of detail into this graph. I'm actually going to put the point right here. 2, 2, 1. Okay? I've added 1, 2, 3, 4, 5 points. That's way, way, way more than enough. Usually you only need 2, especially for absolute value. And then you've basically determined the entire thing. Because notice that about this, this vertex here, the graph should be symmetric. Right? And that just comes out of the natural symmetry of the absolute value function. Right? So this is symmetric. You really only need 2 points. I've given you more than enough because it gave us the opportunity to go through these calculations, and it's also possible that you can get asked to, after graphing this, figure out what the x and y intercepts are. Those are very common questions. Let's just do one more graphing question and then we'll be done for the day. This time we're going to involve everything. Yeah, alright, so let's do 2 absolute value of negative x minus 3, all that over, let's do 3. And plus d, right? So let's add 1 again. It's fine. Okay. So what we need to do first is get it into this form. You may be wondering, isn't it already in that form? Well, actually, no, it isn't. We need to actually get it into an explicit form where you have b as a number. Right now, it's unclear what b is. It's definitely not 1/3, because if it was 1/3, then the x here is positive, but here we have x has a negative sign in front of it. So we need to deal with that somehow. So let's just change our function first. Okay. So what I'm going to do is I'm going to bring out a factor of negative 1/3, and that just turns it into negative 1/3 times x plus 3. Absolute value plus 1. Okay? Just take a minute if this confused you, just to make sure that you're happy with this. You'll see that if you multiply it out, it gives you the exact same thing as that. Okay? So now I've clearly shown what is b. This is b, right? This is a, this is c, and this is d. Right? So let's do our graphing once again. Right? This time I'm going to do the horizontal stretch, the horizontal scaling first, and then the vertical scaling after. So let's take absolute value x. Looks like that. Okay. And then what we're going to do is first stretch it horizontally by a factor of 3. So let's take our good point 1, 1 again and see what happens to it, because that is more interesting than what happens at 0. So if we stretch it vertically by 3, right, it's going to become fatter, much fatter. Okay, still symmetric but fatter. And this point here that is at the same height is going to be just 3 times farther away from the y-axis. So its point is going to actually be 3, 1. Okay? And then usually you have to take into account the negative here because it flips across the y-axis. But because the absolute value function is symmetric, this actually doesn't do anything. It's symmetric about the y-axis. So we're actually fine. We don't actually have to do anything. The next step is to scale by 2 vertically. So we're going to take the y value here and multiply it by 2. So that gives us a new one, which is 3, 2. The point 3, 2. And then I can just draw a line here and then symmetrically draw it like that. Okay. So just to be clear, this is our step 1. This is our step 2. And this is our step 3. Okay. Now we've taken care of all the scaling. All we have to do is take care of these translation effects. So C, because it's a plus 3, it will shift it left by 3, and D will shift it up by 1. So let's translate each of these points 3 to the left and 1 up. On a new graph, okay, we're going to translate those points 3 to the left and 1 up. So here's the point 0, 0. That's going to go 3 to the left, 1 up. That brings it to -3. So I'm just going to write here -3, and then 1 up, so it's 1. -3, 1. Same for this point 3, 2 here. 3 to the left, 1 up. That brings it to 0, 3. 0, 3. Okay? Fill in the lines. Remember, this is the vertex. So the graph is actually going to be symmetric about the vertex. So I can just take this, flip it across, and that's my answer. Like, that's literally all you need to do. Okay? Notice this one does not intersect the x-axis, and it always will intersect the y-axis. Okay? So that's about all I wanted to do for today. You should actually check on Desmos that this is correct. And yeah, make sure that these 2 points are definitely on the graph. That covers pretty much everything I wanted to do today. Next lecture is a really, really important one. We're actually not going to touch absolute value again until, well, for a while. It's just something that is thrown in at the beginning of the curriculum and is used a lot later as a type of example for calculus and advanced functions. But it's important that we cover this early on in the course, or else when we get to it later on, it's not going to make any sense. And we're going to have to make a big detour. So I'd rather get the strange stuff out of the way first. Okay? Yeah, so next lecture is quite difficult. We're going through something that is absolutely new. It's going to involve some pretty intimidating notation. But at its core, the concepts are very simple. And I'm willing to bet that you have a good intuition about them already. So look forward to that. Yeah, that's all I have for today.